Yeah, so hello everybody. Since it seems that one of the subjects of the program is freezing, I have to show something about freezing. So I will talk about a method to get long-range interacting spin chain from dynamical spin chain by freezing dynamical degrees of freedom. And this is a work in progress with Jules Lammers, who will speak next week about related subjects. This work is also related with work that we have done with together with Jules and Vincent Pasquier 2 years ago. So the reason to study long-range interacting models, integrable models, is that they appear in various instances in 2D CFT, for example, in condensed matter, stochastic processes, random matrices, and also they appear in ADS CFT integrability, and this is one of the motivation I have to come back and study this this subject. So there are motivations coming from physics, but also there are motivations coming from mathematics, because these spin chains have, these integrable models have a nice algebraic structure. This algebraic structure is rather rigid, so it's rather difficult to deform this model and obtain the model we are really interested in. So since the models are a bit complicated, we sometimes want to stick to simpler model to understand, to use the solutions that we understand in order to get inspiration to get information about more complicated and more physically interesting, let's say, models. So one of the things that I am interested in is to understand how to connect the methods we use for nearest neighbor interacting spin chains, like Heisenberg spin chain, and the long-range interacting spin chains. And so for one of the topics that is interesting is to see how the method of separation of variables works for the long-range versions of the spin chain. So here I will present a particular particular result on the study of the eigenfunctions of the isotropic Haldane-Shastri Hamiltonian, and this method is potentially usable for other deformations of other spin chains. So first, probably not everybody here knows what the Haldane-Shastri Hamiltonian is. It was defined in the 80s independently by Haldane and Shastri. So it was initially defined for SU2 spins in the fundamental representation, which are on a circle with periodic boundary conditions. So the spins are situated on the, you can imagine that they are on a periodic lattice, and the positions are the roots of the nth roots of unity, if they are on the unit circle. They interact with the usual exchange Hamiltonian, which can be written as a spin permutation. And unlike the Heisenberg Hamiltonian, the exchange is not between nearest neighbors, but between any spins on the circle, and the spins interact with this potential, which is 1 over sine square of the distance between the particles. So since one can construct the spin permutation also for SUN spins in the fundamental representations, most of the things that I am going to see here go through SUN. So this model has many interesting properties. In particular, the spectrum is very degenerate, and the chain has Yangian symmetry. So the Yangian symmetry and how it carries over at the CFT limit. So the CFT limit will be the so you are looking around the antiferromagnetic state of this this Hamiltonian. Well, here the sign is such that that the Hamiltonian is ferromagnetic, but you can, of course, you can change the sign of the Hamiltonian to look at the excitations around the antiferromagnetic limit. So there, the physics is described by a CFT. So in this paper in '92, the Yangian symmetry and the CFT limit were conjectured by this group of people, Haldane and Bernard and Haldane and collaborators and people from Saclay. So the algebraic structure of the Hamilton of this model was sorted out by Haldane together with Bernard Godin Pasquier. And the way this the structure carries over in the CFT limit, in the CFT with SU2 symmetry was clarified by us with. So the description, there is a description of the conformal field, this conformal field theory in terms of spin-ons, which are in fact the excitations of the spin chain around the antiferromagnetic state. And this model belongs to a family of integrable models. So it is in some corner of a parameter space. One can replace this potential between potential of interaction between spins by an elliptic function. So this would be a deformation of this 1 over sine square. P is the Weierstrass elliptic functions. It has two periods. When z goes to well, z plus n here, and another period is complex, and this period can be used as a deformation parameter, and it interpolates. So when kappa goes to 0, we get the very symmetric model Haldane-Shastry. When kappa goes to infinity, one gets the Heisenberg model. In the middle, well, you have some complicated model which is not yet completely understood. One particular limit of this model is better understood when the size of the system, the number of spins, is infinite. Then the potential becomes hyperbolic, and you see that you can go from one potential to the other by analytically continuing n to I pi over kappa. And the nice feature of this Hamiltonian is that you can follow what the integrable structure from Heisenberg to all the way to Haldane-Shastry. So I was saying that the spectrum is very degenerate, very simple, and the spectrum of this Haldane-Shastry is given in terms of motifs. The motifs are a collection of integers between 1 and n-1. So the integers are represented by these dots in occupation of, if you want, of some orbitals. So the energy is given by this very simple function of these numbers, and the only restriction for the occupation number is that the distance between two different occupied orbitals has to be equal or greater or equal to 2. So if they were fermions, you could occupy any of the orbitals only once without restriction. Here you can only pack them two sides apart. And this is a kind of exclusion statistics. It's a generalization of fermionic statistics to a more general exclusion statistics. And in fact, this is what these quasi-particles are like the magnons in the Heisenberg model, except that they have a much simpler type of interaction, and this is helped by the long-range potential. And this, if you look at if you try to count the number of states that you can generate with these rules, you see that there are not so many of them. So in order to span all the Hilbert space, you have to find the states somewhere. So each of this state comes with a huge degeneracy, which is given by the Youngian generators. So it is interesting to see how to relate these energies here, or the motifs to the solutions of the beta equations for the XXX model. So this can be done through the passage through the Inozemtsev model. So as I said, the model simplifies when n goes to infinity, and the potential becomes this 1 over sine square of the distance. So you can analytically continue the root of unity to some real parameter, which is small when kappa goes to infinity. So when kappa goes to infinity, you are close to the to Heisenberg model, and you see that this the potential exponentially diminishes when the distance between sites is large. So this type of property was used like almost 20 years ago when the ADS-CFT activity started, ADS-CFT integrability activity started. So we use this kind of model to match the dilatation operator of the n equals 4 super Yang-Mills theory. So for the first few orders in this parameter t, it works, but then the model, the ADS-CFT model, integrable model is slightly different, but still we can get inspiration from this this kind of deformation in order to understand the properties of long-range spin chains. So what happens when n goes to infinity? We retrieve a kind of Bethe-Ansatz solution. So the values of the quasi-momenta for the quasi-particles are given by the Bethe-Ansatz-like equation, where kappa is some scattering phase, which is given in terms of quasi-periodic function. Now, so phi of p is now plays the role of rapidity. So phi of p for this model is a kind of periodization, quasi-periodization of the rapidity of the Heisenberg model, which is given by this function. So there are two representations of phi of p which are adapted for kappa large or kappa small, and for close to Heisenberg, you have this kind of expansion, and close to close to the Haldane-Shastri limit, this representation is more adapted, and you see that when kappa goes to 0, these cotangents become step functions, and almost everything disappears except for this term and some constant. So the Bethe equation take a very simple form, which is momenta. Well, the scattering phase becomes just a heaviside theta function, the heaviside function of the difference of the momenta. And then you retrieve this quantization condition that we have seen for the motif. And this repulsion, the repulsion of the momenta is given by this interaction here. So this is how you get one model from the other. This phi is essentially the zeta function, the Weierstrass zeta function. So periodization of the cotangent of P over 2. Previous slide, yes. Yes. Yeah, well, this is for few particles. What happens? Yeah. No. No, I don't know what happens, but yeah. Okay, so what? So this function, the rapidity function now is, of course, periodic with respect to P, but is quasi-periodic with respect to kappa. So it's interesting to look to follow what happens with the bound states of Heisenberg. So this question was studied already in '96 by Dietrich and Inozemtsev, and was rediscovered 2 years ago by Rob Klabers and Jules Lammers. So if you take the simplest example of a bound state of 2 magnons, so the bound state is a solution with imaginary part of the momentum. You see that there are 2 types of bound states. The first is the one that we know from the Heisenberg model. You have two momenta with the same real part and the opposite imaginary parts. But when you diminish kappa, you see that Q comes close to the quasi-periodicity limit, and then when it hits the quasi-periodicity limit kappa, the bound states become of different nature. They start to, well, they keep the same imaginary part kappa, but the real parts start to split. So if you follow this critical value of P, where this happens at small kappa is of the order of kappa. So you see that at small kappa, one of the real parts is is trapped close to P equals 0. I'm sorry. And one of the momenta vanishes, and the other stays finite. So what happens is that this state becomes a descendant of another state, because you have a P equals 0 magnon. So P equals 0 means that you have a magnon with 0 energy. So it's a symmetry of the of your spectrum. Okay, so that was about the relationship between Heisenberg and this model. Now the way to solve, I would talk about the way to solve find the algebraic structure and the eigenfunctions of Haldane-Shastry. So the most elegant way to solve this model was proposed by Bernard Godin, Haldane, and Pasquier. It goes through studying generalization of dynamical generalization of Haldane-Shastry, which is Calogero-Sutherland with spin. So you have this interaction. Now these are coordinates on the unit circle that can vary. They are not anymore roots of unity. The particles have spin which interact with this exchange term here. There is a kinetic term, and there is a parameter, continuous parameter beta. Let's take it real and positive. And when beta goes to infinity, you see that there is some potential which tends to trap the particle in the minima of the potential. So the minimum of the potential, which is beta square times this function here, are the roots of unity. So this is what is called freezing. When you send beta to infinity, particles tend to freeze to their equilibrium position, and this spinless part becomes just a constant, and the kinetic term, of course, vanishes, and what is left is just the exchange term with the fixed position of the spins. And I consider here two different versions of the Hamiltonian with two different sides, because it will be important to. There are two different conditions on the wave function which will correspond to the two signs of the exchange term. So this model is solved by using what is called the degenerate double affine Hecke algebra, which involves the collection of positions of the particles and some generalized momentum operators, which are defined in terms of coordinate permutation. So K operators permute the coordinates of the particles, and they depend on this parameter beta, of course. Different operators D, which are called Dunkel operators, they commute. The positions of the particles commute, of course, but between them they have some particular commutation relations, and there is some algebra between the permutations and these operators, which are so the Dunkel operators are covariant under permutations if the permutations are far away. Well, are invariant, and then there is some defect of commutation when they are close to each other. Yes. Here, there is this is. Yeah, it's Calogero-Moser with spin. Yeah, yeah, and this. Yeah, everything raised up, and this this freezing procedure also works for the elliptic model. There are also Dunkel operators for the elliptic model, but they are more complicated. Maybe Jules will mention something about them. So some parts of the story go through, but some doesn't go. So yeah, okay. I will mention what doesn't go through. So what is remarkable about this? What is nice about these operators is that we know what their joint eigenvectors are, and they are called the non-symmetric Jack polynomials. So we can use this information to solve the model. So, but I would like to say something about the space of functions that wave functions we are considering. So it's convenient to take away trivial prefactor in the wave function, which will remove this beta square term here, and then we keep transformed wave function, which we can impose to be symmetric or anti-symmetric with respect to simultaneous permutations of spins and coordinates. So the plus sign, I call it B, bosonic, and the minus sign, the function with the minus sign, I call it F, fermionic. So psi tilde, this space of function, in fact, this is a type of functions with prescribed symmetry. It will have some spin part, which is given by the basis of states where spins are reversed at some positions of the spin chain. And then there is some coordinate component, which will be completely symmetric or anti-symmetric on two groups of variables. So the one group of variables corresponds to the indices that are reversed here, and the other group is the complement. And in order to impose the symmetry, one has to take a linear combination with some prescribed symmetry factor here. So one can work with either with one or the other type of wave function. So but you have to stick with a single one. So on this space of function, one can define a projection which transforms a coordinate permutation into a spin permutation following this condition here. So you get one of these Hamiltonians here by taking the bosonic or fermionic projection of the Dunkel operators, which you have here. You see that they contain only coordinate permutations. So when you do this transformation, you transform your Hamiltonian into a spin Hamiltonian. So why to do this complicated procedure? One of the advantages is that starting from this this projection, you can build a monodromy matrix, which for this model, which looks very much like the monodromy matrix for the inhomogeneous spin chain. You see here you have, for the inhomogeneous spin chain, you would have here some inhomogeneities. Here they are replaced by the Dunkel operators, which commute, so that the algebraic properties, the commutation of these objects is essentially the same as for inhomogeneous spin chain. The only thing is that you have to care that the projection, the projection commutes with the so when you act with elements of this monodromy matrix on a function with prescribed symmetry, you keep this space invariant, and this is the case indeed. So see that this is a trick which allows to incorporate the long-range interaction of the spin chain into this structure of algebraic structure of the model, which is Heisenberg-like. Now, from this monodromy matrix, rather from this one, I will concentrate from now on. I will concentrate on the minus sign here because it's more convenient for what I want to do. So what I wanted to say, add here, is that once you have this monodromy matrix, you can get the integrals of motion by expanding the quantum determinant in powers of u. So essentially the commuting Hamiltonians are given by the projections of symmetric sums of Dunkel Dunkel operators. And since the quantum determinant commutes with everybody here, you see that the integrals of motion commute with everything, and this is the explanation for this huge degeneracy in the spectrum. So now I would like to come to the technical point that I wanted to show how to obtain the wave functions from this freezing procedure. So in order to do this, it's useful to employ a basis of an antisymmetric basis of function of coordinates and spins. So at each site, I introduce some vector which will be a power of z. So k. There are three integers here. One is k bar, which can take any value, any integer value a priori. There is k underline, which can take n values. For SU2, it will take two values, 0 or 1, or up and down. Well, the coordinate dependence is given by these monomials in the coordinates. So the two type of integers are packed together into this other integer. So for example, to get back the usual representation of states, you see that whenever k is a multiple of n, you will get polynomials times the up state and so on. You have n different type of states depending on spin. And if you want to consider an size n system, you take an antisymmetric combination of this function set vectors at each site. So you get a basis of wedges or Slater determinants, if you want, characterized by a collection of integers corresponding to each site. And these integers, because of this antisymmetric nature of these vectors, have to be different. And of this definition, at most n consecutive integers momenta, if you want. These are like these case bars are like momentas. So at most n consecutive case can be equal. And the action of the Hamiltonian on this wedge basis is triangular. So there is the energy can be read on the coefficient of the highest wedge, and then so there is a partial ordering on the wedges, which is very similar to partial ordering on the partitions. But yeah, so the second part of the action of the Hamiltonian is so on which each wedge the action will be will do the following. It will diminish. So if you take a pair of sites, I and j, the action of this bilocal term will diminish the momentum of one wedge by r, and it will increase another one, so that they become closer to to each other. So this kind of action is called squeezing, and there are some coefficients. And you see that in fact, the action of the Hamiltonian on these wedges depends only on the momenta k bar. Also, the energy depends only on the momenta k bar. So the spin is somehow, the action of the Hamiltonian is blind to the spin structure. When we do the freezing, only this linear part here survives. So if we look at the Hamiltonian, we will get an expression like this, and the corresponding energy is given by this linear term in beta here. That's relatively easy to see. And now I would like to explain quickly what happens with the wave functions. So we use a collection of identities when the z's go to root of unity. So the potential, the evaluation of the potential goes to some numbers, which is also the ground state of the Calogero-Sutherland Hamiltonian. And then we see that since the moment we go on a lattice, the momentum has to be periodic. So we shouldn't consider momenta which are too high, higher than capital N. And so the maximum degree of polynomials in each variable should not exceed n-1. And what happens to the symmetric polynomials is the following. The symmetric polynomials can be written in terms of symmetric sums. And we see that when we send z's to roots of unity and we sum over, most of the symmetric sums vanish, except for k equals to 0 modulo n. And also the elementary symmetric sums vanish almost everywhere, almost for every k. And in particular, this relation here means that if we separate the symmetric sums into two groups of variables, let's say z alpha and complement z alpha, where alpha is a collection of indices, the symmetric sums become one the opposite of the other. So if we use all these properties here, so just for simplicity, we'll look at the SU2 case, where there are two types of integers. So these momenta are split into groups, ones which correspond to spin up and the other which correspond to spin down. So this will be the equivalent of the correspond to the magnons. And from this collection of integer, ordered integer, one can define some partitions with, well, some partitions, which are, whose parts are weakly ordered. So with this notation, one can write the wedges in the following way. We have the spin vector with spins down at position I1 to IAM. Then the coordinate part can be split so into group. We have this the antisymmetric part on Z alpha. So this will be some Vandermonde of the variables in the set alpha times the Schur polynomial associated to this partition, and on the other, on the spin downs, on the spin up, we also have some Vandermonde with some Schur polynomial, and then we have to antisymmetrize on the when we change the component of the spin. So when we send the z's to the roots of unity, there is a nice relation which says that the Vandermondes on the sets alpha and alpha bar are related by this relation. they are equal up to some constant and some slightly non-trivial factor, which is given by the product of roots of unity. And also, given this relation that I have explained here, we know that the Schur polynomials for the complementary set will become is proportional up to some coefficient which depends on the partition to the Schur polynomial of the conjugate partition where the lines and the columns are inverted. So we know what this becomes when we send everything to the roots of unity. So we want to transform all these coefficients here into symmetric polynomials with respect to the with respect to the variables of the magnons. So when we do all this thing, we get some zi minus zj minus zk to the power 2. So we have one from the up spin, one from the down spin, and then some. There is this funny factor here, and then product of two Schur polynomials, and product of Schur polynomials can be also expanded on the basis of Schur polynomials. So we see that if nu is not the empty partition, we in fact are generated functions which are linearly dependent of what we already have. So we can safely assume that the nu is the trivial partition, and then nu was related to the distribution of momenta for the C of spin up by some relation. So if nu is trivial, then this distribution of momenta for the up spins is fully packed. And by squeezing, we cannot we cannot touch, we cannot move the momenta by squeezing, by this operation here, because we will encounter another wedge, and this will vanish. This will the corresponding. Constant on Z, but it depends on, no, it's constant, it depends on N. Sorry? Oh, yeah, okay, sorry, it's here. But since I want nu to be, yeah, I forgot the J nu, but since the argument, I mean, it's just to see that we need to have nu equals to 0. So in conclusion, if we do this construction, we have to keep a C of I mean, this momenta fully packed, and we can ignore this part of the wedges and just keep the part which comes from the down spins. We have to shift it a little bit to have a nice properties, but we can reduce the rank of the wedges by 1, so we get an action of a Haldane-Shastri Hamiltonian on UK. It can be translated to the action on these reduced wedges, and if we compute the result, it's exactly the action of the dynamical Calogero with beta equal 1 on some reduced space. So the conclusion is that Haldane-Shastri can be reduced to a dynamical Hamiltonian with beta equal 1 on a reduced number of variables on the magnons. So to recap, we reduce this functions of two sets of variables to a function of a single set of variable. And this function of a single set of variable is given by prefactor to the power 2 times. So now if my Hamiltonian here was fermionic with beta equal 1. So if I transform it into a bosonic symmetric Hamiltonian with beta equal 2, we'll get this kind of wave function. So this one was derived in a different way by Bernard Godin, Haldane, Pasquier. So this is a direct following the wave functions, what happens with the wave functions from when you freeze. So these lambdas here are exactly what is encoded into the motifs. So this construction, what we get in this way works for highest weight states. In fact, if we are coming back to this expansion here, you see that if you are starting to reverse spins and move some of these numbers here from the set of up spins to the set of down spins, in fact, the degree of this polynomial here, the maximal degree in each variable, reaches n. Or exceeds n, so the states, then we have to replace z to the power n by 1. So this nice structure that we have here is not doesn't hold anymore. So unfortunately, we spent a lot of time trying to find a closed form for the descendants, but it's not easy to get something useful. Highest weight, SU2 and Yangian highest weight. There are two types of generators. So if you want, you have these states here, and if you want to lower the spin, move into inside the multiplet, you have to use B operators at at arbitrary values of the rapidity in order to move into the multiplet. You act with any B, you'll go down in the multiplet. So you'll Yeah, the partition lambda label the highest weight representation, and they label the highest weights. So for each, in fact, your space of, so yeah, probably that I wanted to, well, okay. The values of, the eigenvalues of the D operators, in fact, are related by this shift of beta. And if you look at the what this means for the structure of the, so in terms of the inhomogeneous model, the difference of theta would be equal to the inhomogeneity. This will be equal to I. So this is the wrong the relation between thetas that you want to avoid, because at that value you have a fusion of, in fact, a fusion of representations, and some representation will decoupled from from your space of states. So this if you want to think in terms of inhomogeneous model, this is the wrong case to look at, because this is where the pathologies happen. But for the Haldane-Shasti model, that's the interesting point. So, okay, I would like to conclude. So, similar result goes for SUN. You just reduce reduce the dynamical degrees of freedom to SUN -1. And one of the reasons that we look at wedges is that they are nice to look at the low energy limit, because the antiferromagnetic state is particularly simple. It's just a sea of spin downs and spin ups closely packed. And we would like to apply the same thing, the same type of method to a model that we have studied with Jules and Vincent recently, where almost everything that I discussed here goes through. So the model is a XXZ-like deformation of Halden-Shastry with a parameter, deformation parameter, which is Q. So the eigenfunctions that we get are McDonald polynomials with a special value of the Q and T parameters. And instead of having this Zi minus Zj factor, we have this Q van der Monde factor. So this model allows to explore a bigger space of parameter. In particular, the model at Q roots of unity is particularly intriguing because the spectrum is even more degenerate than what we have in Halden-Shastry. And well, it will be nice to understand this kind of model. So for the subject of separation of variables, what we wanted to see what is the equivalent in this framework. The problem is that well, not the problem, but we have a model with the which generates the integrals of motion through the quantum determinant, but in fact we want something generated by the trace. So in order to get something similar to the usual XXX model, we take as a generator of conserved quantities a twisted version of the trace. So when x is 0 or infinite, the trace becomes A or D operator, and then we are back on the previous Halden-Shastry case because A and the quantum determinant commute. Yeah, that's a intermediate model that might have interesting properties. So this is a project that we were doing with Gwenaël Ferrando and Jules Lammers and Fedor Levkovich-Masluk. So okay, I'm sorry for being over time. Thank you very much.
Any question?
Sorry, I think I always ask about the same question, but there is this diagram of models.
Yes.
And then at the end, you have this Q deformation that.
Yes.
Do we have a Q deformation elliptic version that goes to XZ?
Yeah, that's a very good question. Also, Jules is working on this, trying to. Jules and Rob thought a lot about this kind of deformation. I think it's easier to think in terms of this this limit because you can again you can try you continue, you start from the Q deform Halden-Shastry and you try to do a deformation to this to go to this model, and here you control better what you are doing. But if you want to go back to the periodic lattice, that's a little bit more complicated. There is no answer for the moment. But yeah, of course, if you there are a lot of deformations that you can do, but it's much harder to have information about them because even here the algebraic structure is is completely unknown. There are a few Hamiltonians that you can show that they commute, basically 2 or 3 Hamiltonians that higher integrals of motion, but otherwise there is no way to systematically generate the integrals of motion in this way. Here you can use analytic continuation to transport almost everything except the Youngian symmetry. The Youngian exists, but it doesn't commute with the Hamiltonian.
Other questions? It's fine.
So I'm wondering, is there some kind of quantum inverse scattering method to construct all these eigenstates of Bodin Shastri? Because right now you're doing free one way. It's possible to construct in terms of quantum.
Yeah, the problem is that B operator commutes with the integrals of motion. Yeah, B only makes you travel inside the multiplet. So this is why we were trying to define this hybrid model, which sorry, well, it's okay. So this hybrid model will have something like a beta ansatz construction, but then you have to, what it does is it takes all these degenerate eigenfunctions in a multiplet and mixes them. So, okay, that's, yeah, it splits. So you'll have some kind of beta ansatz inside, but inside of each of these multiplets.
We can give up microphone, maybe.
But maybe you remove the mask to that I.
Why is the space
By it's yeah, so it's yeah, so the conformal field theory is not the Halden-Shastri model. It's just what you get when you look at one. Let me try to. How can I go back? No.
I may try this.
Yeah, probably it's better if you push play. And then, so let me go back to the motifs. So yeah, the CFT is not identical to Halden-Shastri, but when you look at CFT, is concentrating on the end of this of such a motif. You send this end to infinity, and you linearize this dispersion relation. Then you have so the energy becomes linear. Then you have strangely, yeah, you have the higher conserved quantities are still there. So they show up in this. Yeah, so you can look here or you can look here, and you will get 2 different sectors. But yeah, it's yeah. Yeah, but as far as I know, nobody succeeded to put them back. Once you start from the two CFTs, put them back in order to get this the middle of the parabola here, if you want. Yeah. 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 Yes.
Not only but it's associated with the motifs is the complementary.
Yeah. Yeah, the limit Q goes to 1 is very degenerate on the level of vertex operators and so on, the algebra. On the finite spin chain, it doesn't seem to be problematic. Yeah, so I don't know how to give a good answer to your question, sorry.
Now we reconvene at 11:50.